So this is the second video about how to solve a nonlinear autonomous system. Um, so and it's a pair of population models. We don't really know what they do yet. We got some ideas, but not quite totally sure. Okay, so the next step, I just calculated the Jacobian. The next step is to evaluate that Jacobian at each critical point and find the phase plot for each critical point. So I rewrote the Jacobian here. And I wrote this little thing over here. If you really understand what a partial derivative is and what it means to linearize a multivariable function, um, and what x prime equal ax represents, then it should make total sense that we use this for the matrix to to do it for all the spots where the derivative is zero, where the x prime and the y prime are both zero, right? Those are spots where if this population system were to start at one of those, it wouldn't leave it because the derivative would be zero, right? Um, so, and I encourage you to try to find the Jacobian for this thing, right? X prime equals 5x plus 3y, and y prime equals 2x minus y. That's one that I just made up. That's one that you could do eigenvalues on. It might be messy, but you could do it, right? And then notice, look, the matrix A for that is 5, 3, 2, -1. And that kind of gets into this, right? And if you understand what a partial derivative is, then it should really make sense what's going on. But that's not easy. So all right, so 0, 0. Some of these are easier than others. 0, 0. That's a triangular matrix. Why is it a triangular matrix? Well, because this piece is 0. That piece being 0 there, 0 there also makes it triangular. What do I do when I have a triangular matrix? Well, the eigenvalues are the entries along the diagonal. So the 14, I subtract it from both of them, gives me 0 here and 2 here, so I get that 2. So I take 1, 0, that's my vector. 16, similarly, I get a -2 here, which gives me the vector 0, 1. You may say, why is the vector 0, 1 though? Well, because if I zero out this column with that guy, I can multiply this by anything other than 0 because I can't take a trivial eigenvector. But so we just write 1. I could write 0, 5, 0, 10, 0, 100, 0 pi, whatever you want to do. 0, 1 is standard. So what's the phase plot for that look like? It's just the source node. I've got two positive eigenvectors, eigenvalues. And the vectors are the x-axis for this one, the 14, and the y-axis for this one. I'm not even going to distinguish between which one would grow faster because it really doesn't matter in this context. We'll piece that together later on. So next one, 7, 0. That's one of my other critical values. So I showed some of the math here for plugging that in. Here is the Jacobian. I'm plugging x equals 7 and y equals 0 in. So really this guy's 0, that guy's -7, and I got to evaluate these two pieces. So you can see me plugging them in there. I get -14, -7, 0, 9. Hey, look at that. It's triangular again. So the eigenvalues are again the entries on the diagonal. I don't have to do that work. -14 and 9. On the -14, I add 14 here. And I get zeros here and numbers here. Really, I don't even care what those numbers are. All I care is that I get the zeros here. So I can do a 1, 0, because that'll zero everything out. 9, I subtract 9. This piece goes away. That guy turns to a -23. I get this. Notice this sort of the same number here as there. It's not a coincidence. But anyway, then I take 7, 23, because that will multiply this by 7, that by 23. I need one of them to be negative because both of these are negative. What does that give me? It gives me a saddle. On the x-axis, I'm going to sink in with this negative. And along a vector 7, -20, you may say, what? 7, -23? All that matters is that it goes over a little bit and down a bunch more, because 23 is a lot bigger than 7, and this would have a negative slope. So I'm not putting a scale there. I'm just kind of making it sort of steep and calling it good. So next part, 0, 8. Bam! Triangular again. How nice. Um, Same process. I'm not going to walk through all that, but I get a vector. This one, I wind up getting 22, 8, right? Kind of like a flip version of that. So instead of being steep up and down, it's steep side to side. 4, 6. This guy's the most work. I think that even on a well set up problem like this, you are going to run into some of these where it gets messy. And this is it for this problem. So 4, 6. When I plug all those in, I get -8, -4, -6, -12. Um, all nice even numbers, but we do not wind up in happiness here. This guy, after you do your trace and your deet and stuff like that, and then let me walk through what I did here. You can complete the square, or you could use quadratic formula, or you could graph it on your calculator. I just like completing the square, so that's what I did. Um, Completing the square, like quick me tells me if it's going to be imaginary, and then I can usually stop. But anyway, complex, imaginary, other one, it's complex. All right, so I got a 20. And then I say, what do I complete the square with on a 20? Well, I divide 20 by 2, actually more this line. I divide 20 by 2, and then square it. So that's 10 squared, which is 100. So just write my 100, right? And then from there, this piece right here is there to balance it so that this 100 with this piece is the same as a 72. So I got 100, I got to go down. That's why I do a minus. And then minus 28 gets me to the 72. So from there, I move the 28 over to the right-hand side. It's positive. That's nice. That means I am not dealing with a complex number. Although I just sort of said that it's nicer when we are, but whatever, I don't care. This is a good example to show you what to do. So I square root plus or minus that right there. And then I move the 10 over. Be careful that 10 is negative because we subtract it. I get negative 4.708 and negative 5.291. That's going to be a sinc node. I know it's going to be a sinc node because I've got 2 negative eigenvalues. Sometimes you can like stop in these scenarios once you know that, but I'm going to go forward because we need to know what it looks like. And I also want to use this as an opportunity to demonstrate how to deal with these decimals because people do not like decimals. I don't like decimals. But you'll see how it works out. All right, so I'm taking that 4.708 and I'm just rounded to 4.7. The accuracy doesn't matter. Remember, my goal here is to make a phase plot. The phase plot is it's an approximation for what happens. It's an approximation to a problem that I can't solve in another way. So yeah, 4.7. So I add 4.7 along the diagonal here and here, right? I get that and that. The -4 and the -6 are the same. So you may be like, oh, right? There are a couple ways to do that. One, you can do it the way that I've taught you all along. Switch these two and negate one of them, right? So that gives me a positive 4, that's the negate, and a negative 3.3. The other way you could do it, some people like to have one of them being a 1, because then you can see the slope a lot easier, right? When you're making the phase plot here. But if I divide, let's see, if I divide the 4, sorry, if I divide the 3.3 by the 4, right? Then I get this point. I think that's a 825, right? So if you like to have a 1 there, then you can have the 1 and then a 0.825. What I want to point out is that is part of why it didn't really matter that I rounded to a 4.7, right? To a single decimal. I'm just going to check this. I know that what I did there works for the top row. Now, if I've done all my work correctly, then it should also work for the bottom. That's what eigenvalues and eigenvectors are, right? So if I take this guy and multiply it by 4, that's 4 times -6. And then this guy and multiply it by that guy, minus 3.3 times 7.3. I get 0.09. that's like close to 0, especially consider that I rounded, right? So very close to 0. So you should see that, well, it works for the top row, and it is so close to working for the bottom row, and we probably lost that piece by rounding. We're good to go. It's probably good for you to do those checks for a little while. So then I do it for the negative 15. I do the same thing. And I get a sync node, right? This one is 4 and negative 3.3. That's this one. It's the one with the negative slope. Here they're both positive, so it goes up and down. It's a little steeper in the y because that's 7.3 versus the 4.3. It's got a slope of like 2-ish or something like that. So we got that, and I am gonna stop here. And the last thing we're gonna do is put all this together, and it like comes together so well and so nicely, and it makes me so happy. See you in a moment.